All right, so let's just jump right in. Oh, come on, come back. Come back. There we go. So we're talking about thermodynamics. So thermodynamics is the, hopefully, obviously, the physics of thermal energy. And like I said with regards to geometric optics, thermodynamics is also remarkably useful in the real world. You know, like firing cannonballs at Mach 2 isn't particularly useful, but thermodynamics is actually a very relevant thing to know about because it tells you how, both in chemistry, how you can talk about heating and cooling and the reactions being exothermic, endothermic, and so on. And it can also tell you about engines and refrigerators and cooling cycles and things like that. So for engineers, it's particularly useful. So I need to give you a few definitions that we're going to use a lot when we talk about thermodynamics. So the first is the phrase thermal contact. So thermal contact is when two systems are allowed to directly exchange energy with each other. So that means if two things can exchange energy, they are in thermal energy, they are in thermal contact. The second phrase is thermal equilibrium. And that is, thermal equilibrium is reached when, sorry, I can't write, when two systems in thermal contact, meaning that they are able to exchange energy with each other, exchange zero net thermal energy. So to put it another way, if two things are in thermal contact, which means that they're able to exchange energy with each other, but they're not exchanging energy, then they're in thermal equilibrium with each other. So let's just jump right in and talk about the Zeroth Law of Thermodynamics. Stop scrolling. I think it's my fist that's doing that. Zeroth Law of Thermodynamics. So the law is as follows. Two objects in thermal equilibrium with each other have the same temperature and vice versa. So this is almost a nothing statement. It's kind of how we define when two things, it's very nearly a definition, but it is an observable fact. If you measure the temperature of two things and they are the same temperature, then those two things, if they are in thermal contact with each other, then they are in thermal equilibrium. And the reason I say that this is almost definitional is that it almost seems obvious, right? Temperature itself is an indicator of whether thermal transfers will occur between two objects in thermal contact, right? It's kind of, it's not quite how we define temperature, but it is one of the things that temperature is used to do. And we have the intuition for that, right? If two things are hot, if one thing is hot and another thing is cold, and you put them next to each other, you can expect that the hot thing will transfer energy to the cold thing and heat it up. That's kind of intuitive. But it's important that we actually know what temperature is and how we measure it. So let's talk about how we measure. Like, how do we actually do it? Like, sticking a thermometer is fine, but you might not know how a thermometer works. So what we're going to talk about is if you were trapped on a desert island and you needed to measure the temperature of something, how would you do it? So before I explain how we measure temperature, we should talk about relative temperature scales. So at the moment, because we're only talking about thermal equilibrium and things not being in thermal equilibrium, we only care about temperature differences. Meaning we don't care if the temperature of one thing is 100. We care if the temperature of one thing is 5 more than the temperature of another thing. We'll get to the absolute temperature scales later, but for now, it's enough to just talk about relative temperature scales. I.e., it's good enough to only discuss relative temperature. So the way that we do this, the way that we set up a relative temperature scale is we just pick a reference temperature, or rather 2 reference temperatures. So we can make just some arbitrary choices. Basically, what these reference temperatures are going to do is they're just going to tell us how much colder is this thing than this thing, or how much hotter is this thing than this thing. And we only need 1 reference temperature to get, is it colder or hotter? We need 2 reference temperatures in order to get how much colder, how much hotter. So the standard arbitrary choices is that we choose that water freezes at 0 degrees Celsius and water boils. Oh, sorry, these are not the arbitrary choices that we choose. These are the arbitrary choices that I'm choosing. And I should not put a Celsius there. Water freezes at 0 degrees and water boils at 7.5 degrees, right? We can just make that choice. Now, we can call this whatever we want. We now have a scale. Maybe we call it the Blitz. And maybe we write it X degrees BZ. I don't know. We could just do that, right? Like we could just arbitrarily decide water freezes at 0 degrees Blitz and boils at 7.5 degrees Blitz, and that's it. So then the human body on this scale is 2.775 degrees Blitz, right? It just is what it is. We'll talk about how we would measure that later, but the point is you just have to choose 2 reference points, and then you can define everything in terms of those things. That's what it means to have a temperature unit. But right? It's such a good physics name. I hope I get named after something, or I hope something gets named after me. There is a more common choice. That you may be more familiar with. Water freezes at 0 degrees Celsius, and water boils at 100 degrees Celsius. I mean, no, there's nothing qualitatively different about the Celsius scale versus the Blitz scale, right? Like they do identical things. The Blitz scale just happens to be smaller, but you can still measure just as much as you would measure in the Celsius scale. Similarly, this is Celsius. Celsius spelled with an S. This is the one that we're going to use for the most part. We will use Kelvin later. And then there's also Fahrenheit, also known as freedom units. And in that scale, water freezes at 32 degrees Fahrenheit and boils at, hopefully you guys know this, you learned in elementary school if you grew up in the States, at 212 degrees Fahrenheit. Either one's fine. Like they are both completely fine for doing science, or at least for measuring relative temperature differences. Things become more tricky when we start talking about, yes, at sea level, of course, all of these things change at sea level. So I've told you what these reference temperatures are, but that's not enough, right? We need to be able to measure temperatures between those. So what those reference temperatures basically give us is they say, look, if you have something that is in thermal equilibrium with freezing water or boiling water, then we know what temperature it has. We know it would have temperatures 0 degrees Celsius or 100 degrees Celsius. But what if something's not in thermal equilibrium with freezing water or boiling water? Then what? I.e., how do you measure temperatures between or away from freezing and boiling water? What we do is we measure the effects of temperature change. So there are a few different effects of temperature change that we can measure explicitly. So let's talk about those. So first, and perhaps, I don't know if this was the first one discovered, but it was almost one of the nicest. Temperature changes cause changes in gas pressure. So to show this, we can graph pressure versus temperature. For different gases. So I'm just going to draw a schematic of what this might look like. So let's just use some random temperature scale. Maybe we use pascals or something here. And maybe we use degrees Celsius or something here. So what we might see is we might say, okay, well, if we're measuring in degrees Celsius, yeah, let me make this a little bit smaller so then I don't have to draw as far. If we're measuring in degrees Celsius, maybe we test a whole bunch of different gases from 0 to or maybe from -20 to 50 degrees Celsius or something. So we test one gas and we plot it, and we see that the pressure depends linearly on for one of our gases, right? We measure that the pressure, if you change the, yes, it varies linearly based on the temperature. You can plot the points, you see that they form a line. And then we draw another. And we see that we also get, for a different gas, perhaps we get this line here for a different gas. It's still linear, but it's a different line. Perhaps we get this line for a third gas, and so on. Again, linear, but different line. And so what we would see as we measure more and more gases is that they all have different pressure versus temperature graphs at different, but if we were to interpolate linearly, we would find that they all would reach 0 pressure at the same place. Now we can't test that low temperature, that's very, very low, but it does indicate that there's something special happening there. And this sort of experiment was done in the 1800s, 1700s, I think. And they didn't have the type of refrigeration machinery that we did to test very, very low temperatures. So they tested temperatures they could do. The important point is that the relationship between all of these, between the pressure and temperature for different gases, was linear, but the slopes were different for different gases. So the observation here, then, is that the fact that all the graphs converge at a common point indicates or suggests that there is some absolute 0 temperature. I.e., we know that pressure, which is force divided by area, that's if you put a gas in a volume, how much force is it pushing outwards with? It doesn't make sense for gas to pull Like if you fill a balloon with gas, it wouldn't make sense for the gas to pull the balloon inward, i.e. negative pressure from a gas doesn't make a whole lot of sense. So in a sense, that's the lowest that these gas, like the lowest pressure that they can have is 0 pressure. And so in a sense, this temperature would have to be the lowest possible temperature that these gases can have. Because if we were to continue the trend line, that would mean that they would go to negative pressure, which just doesn't make sense. So it's not evidence, it's not proof, but it's evidence that there is such an absolute 0 temperature, i.e. there is a place where you can't get any lower temperature. And so what we do, based off this observation, is that we can redefine our 0 point. I.e. now we have actually a natural choice where to put 0 degrees. So instead of water freezing at 0 degrees Celsius, we define another unit system called the Kelvin. Note, it's not degrees Kelvin, it's just Kelvin, just that. So the way we define it is we define 0 Kelvin is equal to absolute 0, based off of the graph above, and there are other ways to determine absolute 0 as well, that all agree with each other. We define 273.15 Kelvin to be equal to the freezing point of water. At atmospheric pressure and at a certain purity and so on and so forth, right? That implies, by the way, oh, and we make another definition too. We also define, or we choose another set point, that 373.15 Kelvin, okay, let me actually rephrase. So we're creating a linear scale, so temperature should vary with some sort of energy or something like that, so we really only can use 2 points. If it turns out that we can, and that's like saying that a line, if you give 2 points, that will define a line. And if you give 3 points, if those 3 points don't agree, you won't get a line. But what we've done is we've chosen our numbers appropriately, that the third point we choose, which is 373.15 Kelvin, that is going to be the boiling point of water, and that will agree with our choice of line. Basically, we've chosen 3 points that all lie on a line in some sense. And so what we can see is that there's still a 100 temperature gap, 100 Kelvin gap between the freezing point and boiling point of water. All we've done is we've shifted where the 0 is. And so what we can say is that, let me give this explicitly, X Kelvin, which is abbreviated just K, would be equal to X plus 273.15 degrees Celsius. So if you want to transition or translate between Kelvin and Celsius, you just take your Kelvin temperature measurement and add 273.15. Sorry. Sorry, you take your, so I phrased that right, but I wrote it wrong. So I'll just write it this way. One degree Kelvin is, you take your Celsius measurement and you add 273.15. So maybe I'll write it this way. So X plus 273.15 Kelvin is equal to X degrees Celsius. That is the, no, I was right the first time. Yeah, I was right I was right the first time. Sorry, I'm just having a very hard time. It's early. Because I'm looking at my notes and I'm like, that doesn't seem right. But no, this is correct. So okay, let's think about this. So negative 273.15 degrees Celsius is absolute 0, right? If you add 273.15 degrees Celsius to that, or 273.15, you get 0, and that is your X Kelvin. This is actually a terrible formula, so maybe I shouldn't have written it. But the idea is just that Kelvin is always 273.15 degrees higher, or units higher than whatever Celsius you measure. I don't know why that was so hard for me. clearly the concept's not difficult, right? Anyway. Great, okay, so that's one way that we can talk about temperature changes, right? If we had some sort of object that, or if we had some sort of device that had a bunch of gas in it and we could measure the pressure, all we would do is we would take our box of gas and we would put it in thermal contact with something that we want to measure the temperature of. So maybe the temperature of something is unknown, but it's between the boiling point and the freezing point, the freezing point and the boiling point of water. So we would take our box, put it next to the thing until they exchange enough energy so that the box of gas is at the same temperature as the box of, or as the thing that we're trying to measure. From there, we would look at our graph, and we would say, oh, well, according to our graph, which has been interpolated all the way in both directions, we would say for this sample, that would mean that if it has this much pressure, it must be at this temperature. And from there, we could then say, because it's in thermal equilibrium with the other thing, we could say that the other thing has such and such a temperature. So that's one way you can measure temperature. Not the most efficient way, because gases tend to take up a lot of space. And furthermore, pressure is not particularly easy to measure, especially small changes. Another way that we can measure temperature is using thermal expansion, which I will describe here. So thermal expansion is quite literally expansion or contraction of solids or liquids when the temperature changes. So this is great. Like, this is a thing that we can observe happening, and probably has been observed happening for 1,000 years, or even or more, perhaps 2,000, 3,000 years. Greek and Romans, and probably the Chinese and Egyptians as well. But it's not quite obvious why it happens. So first, let's discuss thermal energy. So thermal energy is basically a microscopic manifestation, of random, I misread. It's a macroscopic manifestation of random microscopic motion. And we know that motion, typically, when you have a whole bunch of things interacting with each other, think like a whole bunch of things attached to springs or whatever, motion has energy associated with it, right? Obviously it has kinetic energy associated with it. Anything that's moving has kinetic energy. But also we know that motion, as long as there are forces involved, will have potential energy associated with it as well. The position of the atoms and molecules also plays a role. And if they are moving, that position is changing, hence they will have a changing potential energy. So it's complicated how all of this works at a microscopic level, but one of the consequences of these technicalities and of the explicit calculations that you do when you talk about these things, a consequence of this is that if you have more energy in the bonds holding molecules together, and by the way, this energy takes the form of oscillations in the bonds, the bond length, so you have like molecules oscillating back and forth, right? This implies if you have more energy in the bonds holding the molecules together, then you get higher average separation between those molecules and atoms. So the end result implication is, so we said that the objects expand when their temperature changes. We are talking about temperature in terms of thermal energy, and we'll get to that explicit relationship later. But so if temperature increases, and we say that that implies that the thermal energy increases, that's kind of how temperature is measured, then if thermal energy is higher, then the microscopic random motion would be higher on average. And so that means that there's more energy on average in the bonds holding these molecules together, and thus on average, the molecules would be further apart from each other. The end result of this logical chain is that more thermal energy is equal or is equivalent to having a larger volume. And I should clarify that this is true for reasonably low temperature changes, right? If your temperature increases by 1 degree, then you'll see a correspondingly small change in volume. But if you like quadruple the temperature, the relationship isn't quite that precise anymore, because phase changes can happen and so on and so forth. And in fact, we can express this relationship mathematically fairly easily. And this is a measurable phenomenon, by the way. Like, you can just go out and show that this happens. Once you are aware that such a phenomenon occurs, it's fairly easy to actually determine this relationship. Just heat things up to different temperatures and then see what happens to their size. So what we find is that the change in length divided by the original length, L naught, is equal to alpha times the change in temperature. So here, alpha is a coefficient of linear expansion, or is the coefficient of linear expansion. It's just a number. It has units. The units are given by inverse Kelvin, or equivalently, inverse degrees Celsius. It kind of makes sense. You want both sides to be unitless, because delta L over L is unitless. So we need to multiply delta T by something with inverse units of temperature. And by the way, the reason I say that it's or here is because we're only interested in delta T. Right, so we didn't have to pick a unit. We could use Celsius or Kelvin for delta T, because the difference between two temperatures in Kelvin would be the same difference between those two temperatures in Celsius, because all we're doing to translate between one to the other is just adding a constant, right? It's like saying 5 plus 3 minus 2 plus 3 is equal to 5 minus 2, right? Because I'm just adding the same thing. That's the point I'm getting at. So we can rewrite this equation, but I'm going to put a box around this. So let's rewrite this equation. Stop scrolling. So delta L would be equal to A L naught delta T. And delta L is LF minus L naught, right? L naught being the initial length, the length that you have before you start changing the temperature. And this is equal to alpha L naught delta T still. And so what we get is that the final length of an object after you've changed its temperature is 1 plus alpha delta T times the initial length. This is a useful formula because it tells you what the actual lengths are, not just the change in length. Now, you could obviously have solved for this. That's all we did, but this is a nice formula, and it tells you that the size, if delta T is greater than 0, then the length, then 1 plus alpha delta T is greater than 1, and so the length grows as you increase the temperature. Now that's great, assuming alpha is never negative, and it isn't. Actually, is that true? No, alpha is not always positive. For most substances it is. For complicated substances, it can be negative in some temperature regimes. Note that alpha actually does change with temperature, but over a relatively small change in temperature, alpha is a constant, which is why we can use this relationship. Now, this is great. This formula is fine, but objects exist in 3 dimensions. So they expand in 3 dimensions. Right, they're not just going to change length, they're also going to change height and depth as they grow. If you have like a cube of stuff, it's not just going to get longer, it'll get longer in each dimension. So we need to talk about volume expansion rather than just length expansion. And there's a formula for that too. the reason I wanted to do the formula for the length expansion first is because we use that in calculating the volume, the formula for the volume expansion. So we're going to consider a cube. By the way, the entire computation I'm about to do generalizes for various shapes, but it requires a little bit of differential calculus in order to make this formal for a general case. So we're just going to talk about a cube, and then we're going to find the relationship for a cube, and we'll then relate it to, I will just make the claim that this is what happens in general. Right, so dV, this is a small change in volume, is Vf minus V naught, which is just L naught plus dl. If this is a cube, then each side is going to grow by a certain amount, and if it's a cube, each side will grow by the same amount. So L naught, so it's L naught plus dl cubed minus L naught cubed, right? That's just the formula for the volume of the cube. This is equal to L naught cubed plus 3 L naught squared dl plus 3 L naught dl squared plus dl cubed minus L naught cubed. So immediately we can cancel off some terms. I'm also going to cancel off both of these terms. The reason I'm doing that, and you've seen this argument in calculus or physics before, if dl is infinitesimally small, dl squared, dl cubed, those are even smaller, so we treat them as if they're negligible and ignore them. So what we get is we get 3 L naught squared dl. I'll put an approximation sign here, which can be written as 3 times L naught cubed divided by L naught dl, or 3 times V naught dl over L naught, right? So I just did some rearranging. L naught cubed is the original volume, so I just replaced it with that, and then I divided it, and then I moved the fraction over, basically. But we know that dl over L naught, we know this formula, that dl is equal to A alpha L naught dt, where we're using d instead of delta because these are very, very small amounts. And so what we're left with is that dv is equal to 3 times alpha V naught dt, right? Perhaps more easily put, dl over L naught is alpha dt. That's all we're saying. And so all we do is we just redefine this. We call beta, which is by definition equal to 3 alpha. This is the coefficient of volume expansion. And so then we get the formula dV divided by V naught is equal to beta dt. Now, we use beta and alpha differently. The reason why they have different names is just because they're used in different contexts. Sometimes we might actually be interested in how the volume grows, and in that case, it's just easier just to know what the coefficient of volume expansion is. Whereas if we're just talking about how much longer something gets, which is a very different use case, you might be interested in alpha. That's the only reason why they have different letters, and we don't just say one is 3 times the other. I mean, one is 3 times the other, but that's why they have different variables associated, or constants associated with them. So, why was I talking about this? Well, this is another way, this is another effect of temperature changes. So, with this in mind, we can actually produce something called an expansion thermometer. And these are actually used in old thermostats. And basically, they're formed by creating something called a bimetallic strip. So a bimetallic strip is literally a piece of metal. Maybe this one has a high coefficient of linear expansion, glued or attached in some way, maybe welded, to a piece of metal with a low coefficient of linear expansion. Then what happens when you increase T? Well, that means that delta T is greater than 0. And so what happens is that the longer one tries to get longer by more than the shorter one. And the only way that can happen is by having the strip bend, because that's the only way that they can still be attached at every point and yet have their lengths be different. I.e., this one expands more, and the bottom one expands less. It still expands, mind you, it just expands less than the one on the left or the one on top. Now, this is used in thermometers because, or sorry, in thermostats, because you can adjust your bimetallic strip. You can design your bimetallic strip so that when you turn a dial, which maybe rotates or angles your bimetallic strip, when the temperature difference between the bimetallic strip and your and the desired temperature gets to a certain level, when the temperature difference is sufficiently large, the bimetallic strip will bend, and because it's made of metal, it'll contact something and turn on a circuit. And that will turn on the AC, for example, which will cool the house down, and then it'll bend back because it'll now be at the appropriate temperature. And then once it heats up again, it'll contact again, and so on and so forth. It's a rudimentary way to create a thermostat. You can also use this in mercury thermometers. This is exactly how mercury thermometers work. You have your little bulb filled with mercury. Here, this is linear expansion because it can only expand in one direction. So well, no, I mean, that's not true. No, it's volumetric expansion, but it's forced upwards. So, but the point is you could design your thermometer so that, and you can put little marks on it so that when its temperature increases and it expands, the mercury will go up because it expands, and then you can mark what the new temperature is, and then you can use that to measure it. The reason they use mercury is because it's a metal and because it has high thermal conductivity. I would also imagine it's because it probably has a fairly large coefficient of expansion. Can't say for certain though. So this is how you can measure temperature explicitly if it's not within your standard range. You basically calibrate your thermometer, whether it's a bimetallic strip or a mercury thermometer. You calibrate it so that it's in certain positions at, say, your 2 reference temperatures or your 3 reference temperatures. And then you just say, okay, well, we know that we just put our numbers like 50 degrees Celsius, we would just put halfway between because we know it varies linearly. So it's actually relatively easy to make thermometers, and that's why they've been around for 300 years. Right. Okay, so that's how you measure temperature. Great. We know how to measure temperature now. That's excellent. We know what temperature scales are. Also excellent. But that's not all thermodynamics is about. Thermodynamics is actually about the dynamics of thermal energy, right? So we need to talk about how energy actually goes from place to place. And the most common form that we will see first, anyway, is heat. So let's talk about heat. So you may have noticed, or at least I tried to do this, I tried not to use the word heat when I was talking up until now. Let's talk about temperature changes and energy transfers and so on and so forth. But I tried not to use the word heat. If I did use heat, I apologize because, you know, even I'm susceptible to colloquialisms. So heat has a physics definition that differs from everyday use. And this is the same phenomenon that happens when people talk about a theory, right? A physics theory is different from, or a scientific theory is different from, I have a theory, right? So the point that I'm trying to make here is that thermal energy is not the same thing as heat. Very important distinction to make because you will get awfully confused if you start interchanging those things. So let me give you a definition. So heat is energy that is transferred. It's transferred from one system to another let me slow down, to another due to temperature differences between the systems. Sorry, I'm abbreviating. So we can break this definition down, right, and to try to understand it better, so let's do that. So heat is transferred energy only, meaning it doesn't make sense to talk about how much heat something has. Heat is just an amount of energy that goes from place A to place B. This is only caused by thermal non-equilibrium, i.e. when two things are not at the same temperature, that's the only way that heat transfer occurs. There is no reference in the definition to how this energy is transferred. It's all heat. So any type of energy that goes from one object that is not in thermal energy with another object, where that energy transfer is caused by the fact that they're not in thermal equilibrium, that is called heat. Regardless of how that energy actually got from point A to point B, if it's energy transfer from thermal non-equilibrium, it's heat. And so the point I was making is the first point, that in that heat is not something that an object has. Heat is energy that is transferred. In the same way, almost, that a thing doesn't have a certain amount of power, right? Power is a rate at which energy is either used or transferred. So things don't have power. They use a certain amount of power, or they give off a certain amount of power, right? It's the same way with heat. Either a thing doesn't have heat. It either gets heat from another object, or it gives off heat to a different object. So the SI unit for heat, it is a unit of energy, so it's in joules, just like thermal energy. And all energies have units of joules, we know this. And there are some non-SI units that you might want to be aware of as well that are units for heat. There's the calorie. There's the British thermal unit, also known as the BTU. I don't know why modern house heaters use BTUs, but they do. A calorie, by the way, for those interested, is the energy required to add to one, I can't write in a line, to add to 1 gram of water to bring it up, or to bring it to 15.5 degrees Celsius from 14.5 degrees Celsius. That's just how a calorie is defined. This was a particularly easy way to define an energy for heat, or like in the late 1700s, early 1800s, because we had good and precise ways of measuring temperature, and we had good and precise ways of measuring mass. So if you can figure out how much energy it takes to change the temperature of water by a certain amount, then that's a perfectly fine standard. We just have a better standard now. So the conversions between these might also be useful for you later on. 1 calorie is 4.186 joules. By the way, a calorie with a lowercase c is not the calorie that you see on food. Calories that you see on food have uppercase c's. Those are also known in Europe as kilocalories, kcals. That's 1,000 lowercase c calories. So 1 kilocalorie, or 1 food calorie, is 4,186 joules of energy. 1 BTU is 252 calories, which is 1,055 joules. Right. So I mentioned something about how the calorie was defined. It's defined as how much energy does it take to change the temperature of a thing, and that act of changing the temperature of things by adding a certain amount of energy, that is kind of fundamental to this idea of thermodynamics. It relates the thermal energy of a system to its temperature. So there's a technical name for this study of how heat added changes temperatures, and that is called calorimetry. And the quantity that we measure is called heat capacity. So let's talk about heat capacity and calorimetry. Calorimetry named after the calorie, presumably, or maybe vice versa. So as we've said, an imbalance in temperature in BANTs, imbalance in temperature. Actually, hold on, before I continue, let me stop and ask if anybody has questions before we start talking about heat capacity. I can't tell if somebody's typing something very long or if there are just no questions. I'm going to assume there are no questions then. If you do have a question, I'll stop and answer it, but I'm going to continue. Right, so we know that an imbalance in temperature of two systems implies that you will have thermal energy decreasing in one of them and thermal energy increasing in the other. They will come to thermal equilibrium via a heat flow. Heat flows from one to the other in the direction of hot to cold. So the loss of energy by the hotter system reduces its thermal energy. I'm running out of space. The gain of energy, similarly, by the colder system, increases its thermal energy. So, by the way, the reason we know that is because assuming all else stays the same, that energy has to go somewhere, and it has to come from somewhere. And it's not like the object's speed is changing or the object's position is changing to change the potential energy. It's just a different type of energy. And that energy is what we call thermal energy. It's the energy associated with temperature and random motions in the object itself. So let's consider just a single system instead of two systems. And we're going to do this a lot, where we just consider a single system because it's easier to handle. So how does heat entering the system or leaving the system affect the temperature, right? That's clearly a useful question to ask because we know that that happens. For example, when you put a stove or a pot of water over a fire, there is energy transfer from the gases to energy transfer via heat from the gases to the pot, which then transfers energy to the water. And so we know that the water is going to get hotter. The question is qualitatively, how does this happen? So experimentally, at least for small temperature changes, we find that Q, the amount of heat that enters or leaves the system, is proportional to the change in T. Now, by the way, Q is the letter that we give for the amount of heat transferred. So the fact that there's this proportionality constant, this implies that Q has to be equal to a constant times delta T. Unfortunately, this constant is misleadingly called heat capacity. It is not like the amount of heat a thing can hold. Not sure why it got that name to begin with. It's a historical thing, but that's what it's called. That constant that tells you if you change the temperature by this much, that means you've added or subtracted this much heat. That constant that defines that relationship is called the heat capacity. So let me give you some sign conventions. Again, whenever we have an equation with variables that we measure, it's useful to have sign conventions just like we had for optics. So sign conventions, we have Q is greater than 0 when heat enters the system. That implies that delta T is greater than 0. Q is less than 0 when heat exits the system. Which implies that delta T is less than 0. You may have seen different sign conventions in chemistry. I can never remember which sign conventions chemistry has different from physics, but keep in mind that these are the sign conventions that we're going to use. And if you use a different set, you might get answers. If you use a different set and use equations that I've used that rely on those sign conventions, you might get the wrong answer. Right, so sign convention, or so just like the coefficient of linear expansion or the coefficient of volumetric expansion, it's just a constant and it depends on the material. So, or it depends on the thing that we're measuring. So you might ask, what controls heat capacity? So one thing that I already mentioned is the type of matter, right? That's like the stuff, what it's made out of. For example, the sentence, water takes more heat to change temperature than aluminum. That's a statement about the heat capacity being different for aluminum and water. But another thing, perhaps more obviously, but maybe less straightforward, also the amount of matter also affects the heat capacity. I.e., the sentence, a lake takes more heat to warm than a cup of water. I.e., there's more stuff to heat up. Hence, it would have a larger heat capacity. So we can actually write the equations accounting for the two ways that you can change the heat capacity. And there are actually two ways to do this, and I'll explain why this happens, why we write them in two separate ways. So the first might be written as MC delta T. Okay, now I actually have to decide how I want to how do I want to define these? Because these are always troublesome. I'll stick with my notes for now, but I might end up changing things on you later, in which case I'll tell you. It's just we kind of run out of letters, which is unfortunate. So the first one, relatively straightforward. This is the amount of, in this case, the amount of matter is measured by mass. And so the lowercase letter c is called the specific, I'm going to give this a better name. C is called the mass specific heat capacity. These are all terrible names, and I'm very sorry for this, that the conventions are better. The other formula that we will use is Q equals N capital C delta T, and I hate this formula because it doesn't, usually we use capital C for just heat capacity. But anyway, we're going to use capital C for the other type, where, so here, the amount of stuff is measured in moles. And you guys know what a mole is. You guys have all taken high school chemistry. And so C, capital C, is the molar specific heat capacity. By the way, you will see things called, you will occasionally see the lowercase c, the mass specific heat capacity. Sometimes you'll just see it called the specific heat capacity without a specification of mass. Similarly, sometimes you will see the capital C, which we are calling the molar specific heat capacity. Sometimes you'll just see it called the molar heat capacity. I hate both of those alternative definitions, because the heat capacity is a well-defined thing. The heat capacity depends on the type of stuff and how much stuff you have. So I would say this phone has a heat capacity of, I don't know, 5 joules per degree Celsius. And it has nothing to do with how massive the phone is, what the phone's made out of. It's just the heat capacity of an object. Sorry, that's a picture of my wife, who's very lovely, from our wedding. And so I would say this can has a specific heat capacity of such and such an amount. But then I would go on and say that water, because I'm not talking about a certain amount of water, I would say water has a mass-specific heat capacity. Notice that the word specific tells you that it's per unit something, and the word beforehand tells you what that something is. So water has a mass-specific heat capacity of however many joules per Kelvin kilogram, meaning if you have 1 kilogram, then that 1 kilogram of that stuff, it would have a heat capacity of however many joules per Kelvin. And similarly, if you had 2 kilograms, it would have twice that much of a heat capacity, and so on. Or if I was measuring with the molar specific heat capacity, I would count how many moles I have, multiply that by the molar specific heat capacity of that substance. Doesn't matter how much of that substance I have, it would all be the same. And that would give me the heat capacity of my sample. You might ask, why do we use both? It turns out that for gases, it's easier to measure the amount of stuff in terms of moles. There's a good reason for that, which we'll get into later. For solids and liquids, it's easier to measure just mass. You can just stick them on a scale and weigh them. The reason it's hard to do that for gases is because gases tend to be very, very light, have very, very low mass, and so the buoyancy effect from air is dramatic. And so putting them on a scale, you have to put them in a vacuum if you want to get a good mass measurement. By the way, according to the definition of a single calorie, the following statement is true. The specific heat capacity, trying to use a lowercase c, of water is equal to, I mean, this is just definitionally, it's equal to Q divided by M delta T. And so the specific heat capacity of water in terms of calories, grams, and Celsius is 1. It's 1 calorie per 1 gram per 1 degree Celsius, which is why it's kind of a nice, the calorie is kind of a nice definition, because in those units, the mass specific heat capacity of water, by the way, sometimes I will drop the capacity when I'm talking about this. I'll say mass specific heat or molar specific heat. It's the same thing. The mass specific heat of water is just 1 in those units, which is kind of nice. And so the whole point of this discussion of heat capacity is that it allows us to solve hard problems. Good example of a hard problem. What is the final temperature of water if we dip a hot iron bar into a bucket full of cold water, for example? Like you have water at 20 degrees Celsius and you have an iron bar at 700 degrees Celsius, and the bar has a mass of 2 kilograms and you have 8 kilograms of water. What is the final temperature of the water if you dip the bar into it and you wait for them to come to equilibrium? That's a question that we can answer using this sort of tool. The way we do this is we apply energy conservation. And we use the sign conventions, and the sign convention. So this method of problem solving, or this type of problem that we try to solve using these sort of heat capacity things, this is called calorimetry. And you can imagine why this would be helpful to, or why this calculation technique would have been useful 200 years ago, right? When we didn't have uber precise thermometers, sometimes it was just easier to actually just calculate using formulas. Like if you were a blacksmith and you wanted to make sure that your water didn't boil, how much water do you need? How much water do you need in order to quench a a blacksmith, like there are blacksmiths in the 1800s. But the point is like if you're doing some sort of industry something and you want to figure out how much water you need so that not all of it boils away, then this is the sort of thing that you need to do. Right, so it is true that adding thermal or changing the thermal energy of a thing or adding heat to a thing changes its temperature. That's not the only thing that it can do, though. Adding heat to a system can also cause phase changes, or removing heat from a system can also cause phase changes. And so we need to talk about how that happens, and in particular, we need to talk about a quantity called latent heat. So when heat transfers occur, temperature can change, or the phase of the thing can change, right? Think about putting an ice cube on a stove. The ice cube, if the ice cube is lower than 0 degrees Celsius, it will increase its temperature to 0 degrees Celsius, but then it'll melt. And while it's melting, its temperature isn't changing, and I'll get to that in a little bit. Actually, I was about to say that. So when a phase change occurs, the temperature is constant. So in that case, heat capacity isn't helpful. By the way, one way to see this, how we know that the temperature is constant, is that as long as if you put ice in like a cup of water, you shake it around so that it mixes and everything goes into thermal equilibrium, as long as there's still ice in the water, it's not going to get warmer. Like the water won't get warmer, right? And that's because the ice is undergoing a phase change. And so its temperature can't get above 0 degrees Celsius until it's done with its phase change. And that phase change can take a while, right? It's not that it's lower than 0 degrees Celsius, because if it was, then there would be no water, it'd all be ice. It's not that it's higher than 0 degrees Celsius, because if it was, there'd be no ice, it would all be water. When the ice and water exist together, the temperature is just fixed at 0 degrees Celsius. And that's why ice water is so pleasant and why it's always the same temperature, why it always feels like it has the same temperature, because it's always exactly 0 degrees Celsius, at least approximately, because sea level and stuff. Although I don't think that the freezing point of water changes dramatically with pressure. So fine. How do we measure, if we can't measure it by temperature changes, how do we measure the heat required to change phases? We can't just stick a thermometer on it because its temperature is constant. So we have a quantity that we call latent heat. So latent heat is the amount of heat required for, say, 1 kilogram of a substance to change phase. So the thing is we just don't explicitly measure the amount of heat required to change phase. We just experimentally determine it beforehand. We figure out that if you have 1 kilogram of the stuff going, if you have 1 kilogram of ice going from ice to water, how much energy do you need to add to make that phase change occur? Well, it'll take half as much as if you had 2 kilograms of ice going from ice to water. And then we just say that Q, again, heat, the heat entering or leaving the system, is equal to LV delta M. Here, LV is the heat of vaporization. So think this is the energy required to go to transition between the liquid and gas phases. And then we have, similarly, we have Q equals LF delta M. LF is the heat of fusion. And this is the energy per kilogram required for the solid to liquid phase transition. And here, delta M tells you how much of the substance changed phase, or will change phase if you add that much heat. So in this case, there's a sign convention that I like to use. If delta M is less than 0, that means that we have some liquids becoming solids, or gases becoming liquids. If delta M is greater than 0, this is, by the way, this is just a sign convention. Then we say that that tells us that solids are becoming liquids, or liquids are becoming gases. So the whole point is that you have to add energy to a system in order to get it to change phase to the higher temperature phase. So if I have ice at 0 degrees Celsius, and its surroundings are 100% at 0 degrees Celsius, it'll just happily stay ice. If there's no energy being added to or from it, it'll just sit there being ice at 0 degrees Celsius. The moment that you add some energy to it, well, it can't increase its temperature because it's still ice. So instead, that energy will go towards changing the phase. And so you would go and you would look at the latent heat of fusion of ice, because we're talking about a phase change from the solid to liquid. It's just a number. It's a joules per kilogram, basically. And you would multiply it by how much ice you want to change phase. And so if you had 5 kilograms of ice, the latent heat of fusion of ice, I don't remember what it is, it's some number, multiply that number by 5, and this will tell you how much energy you need to add to the ice in order to get it to become water at 0 degrees Celsius. Because remember, at the freezing point, water and ice can coexist. That's what ice water is. And that's why ice water stays ice water for a good while. Sublimation is a very similar process. It's just, I won't hate for that. It's just some substances at certain pressures just don't have a liquid phase. So instead, there is just a heat of sublimation. That's all. It's just the thing that you measure. Like dry ice sublimates to CO2. There is a heat associated, or there's a latent heat associated with that phase change. So if you take 1 kilogram of CO2 at its freezing point, at its sublimation point, and then you add a certain amount of energy, it's the amount of energy for 1 kilogram being the latent heat of sublimation, yeah, you just plug it in. The point I was making with these sign conventions is that if you want, we know that you have to input heat into a system in order to get it to go from, say, ice to water, or water to water vapor, water to steam. So that means that Q should be positive when delta M is positive. So we define our sign conventions to be that delta M, the amount of stuff that's changing phases, is positive when you're going from the lower temperature phase to the higher temperature phase. And delta M is negative when you go from the higher temperature phase, like liquids to solids, to the lower temperature phase, like liquids to solids or gases to liquids. That's just a sign convention that's very useful to keep track of whether it's positive or negative. Right. Great, okay, that's good progress. So that is what latent heat of fusion is, and it's just another useful tool in doing this sort of calorimetry type of calculation. It turns out that you can actually combine the heat capacity and latent heat to graph a temperature versus Q for a sample of some substance. Basically, let me see if I can get this right. And you'll see these types of graphs pretty frequently when we're talking about thermodynamics. You'll have a graph that looks something like this. You have Q. This is Q. This is heat added to the thing in joules. Then you will have a temperature in Kelvin. And maybe our substance starts at some temperature. Let's just say it starts at absolute 0. So if it starts at absolute 0, you need to get it in order to get it to absolute 0, you have to add 0 joules. So that's one point. Okay. How much energy do you need to add to get it to increase its temperature? Well, we have a formula for that. That's specific heat. We have heat capacity. We have a relationship between the heat capacity, or between the temperature and the energy added. And that is just the formula that's given by the heat capacity. So in this case, we would just have a line. It's linear because temperature is proportional to the change in temperature is proportional to the heat added. And so this line and maybe, by the way, in this place when it's very, very cold, so it's solid. This line is described by effectively T equals Q over maybe MC. And this is the specific, let's use lowercase c, the specific heat, the mass specific heat capacity for when it's in its solid phase, because the heat capacity can change. But then after it gets to a certain point, say its melting point, you can't increase its temperature without adding energy to change its phase first. So in this region of the graph, our sample is solid. Then, if we keep adding heat, the temperature doesn't change. So in this region, the amount of heat added, this is just the total mass of the substance. That's basically how much heat is added. That's the distance from here to here. That is how much heat is added in order to get the phase to change from solid to liquid. So in this case, this would be a mixed solid-liquid phase. And then maybe it's a liquid for a good while, and you just heat it up. Because now it's a liquid, it might have a different heat capacity. So the point is you've added this much energy now. Oh, you've added this much energy now, which is the amount of energy needed to go from absolute zero to the melting point, and then melting all of the solid, making it all become liquid. And so in this regime, perhaps, we have the amount of energy to go from liquid at the melting point to liquid at the boiling point. This would be the temperature is equal to Q divided by the mass. It's the same mass, but now it has a different heat capacity, sorry, specific heat. And so I drew it at a different slope. And the reason why I drew it at a different slope, and maybe there's like plus a number or something there, this is just telling us how the temperature changes. And so the slope here is effectively the heat capacity of the substance. In fact, it's actually the inverse heat capacity of the substance, but that's neither here nor there. So lower heat capacity means higher slope. And then it goes from liquid to gas. So again, we have Q equals mLV, because now we use the latent heat of vaporization. In this phase, it's a mixed liquid gas phase. And a mixed liquid gas phase shouldn't be that surprising. If you like put a lid on a pot of boiling water, there's steam and there's water. So they are coexisting at the same temperature. We never write delta Q. Never, ever, ever write delta Q. I should actually be writing delta T here. But the reason I didn't write delta T is because we know what the initial T is. Perhaps this clarifies. So Q is how wide that section is. And so this is actually Q added. This is the amount of heat added from zero. And then the amount of heat that you're adding goes to the right. That tells you where you end up. The point is after you get to this point, then you can just heat it up forever. In this case, well, not forever. There are plasmas. And then, but then again, we just use delta T. How much the temperature changes is just Q over MC gas. Maybe we use NC gas in this case because it's easier to measure the substance. And so we'll see these kind of charts pretty frequently, where you have temperature versus heat, and it basically tells you a lot about that substance. It tells you how much energy it takes to change phases, how much, and this might be for like 1 kilogram or something. It tells you where the melting and boiling points are. It tells you the various heat capacities and so on. So you can learn a lot from these graphs. Okay, so the last thing that I want to cover, and I think we're making good time, is heat transfer. So we've talked about heat transferring, but we haven't yet talked about how heat transfers, i.e., what actually happens in order for the energy to go from point A to point B. So it turns out that there are 3 main modes of heat transfer. You may have learned about these in high school. So let's talk about the simplest mode first. So the first is called conduction. So the way to think about conduction is that you want to imagine molecules in a solid as being held together by springs. Now this is just a model. It's like they're not actual springs there, but it's a good approximation and it helps us understand what's going on. So maybe you have like your crystal lattice. And they're all held together by springs. So if you were to whack it, they would jiggle around a little bit. So it should be fairly straightforward from this picture that if you vibrate one end, that will cause the other end to vibrate. And in fact, you could even think of these as waves. Well, almost. Turns out you can't because there's energy distribution, but in a sense, you can think of it as like a wave propagating. There's a thing called a phonon, which is a wave, which is basically this happening. Now, say we have a rod touching a stove on one end, and an ice cube on the other end. So I'm going to do my best to draw this. So you have your stove top, right, with your little stove burners. Then you have your really giant rod. And in your giant rod, you have a whole bunch of molecules that are connected like they're attached by springs. Obviously not scale, right? And then you have your ice cube. And I'm going to draw one of those like roundish ice cubes. That looks like toilet paper. Whatever, it's an ice cube. I didn't get a degree in art. So the particles on the left of the rod will vibrate more than the particles on the right. I smell pasta. Am I having a stroke? No, I'm probably fine. The reason for that is that the particles on the left, or the temperature on the left, is hotter than the temperature on the right. And so we know that higher temperature means more thermal energy, and more thermal energy in the region with higher temperature. And so you'll have higher vibration or faster vibrations. And similarly on the right, you have lower temperatures, so less thermal energy, so less vibrations. So that means that the particles on the left will start making, you know what, that's possible. I should, I'll go check later. That means that the particles on the left are gonna shake the particles on the right. More like eventually the vibrations on the left will cause the vibrations to travel down and will eventually get to the right. And that's conduction. So you might ask, how fast is energy transferred through the rod or transmitted? So we're going to do some calculation here, or we're going to do some modeling here. We're going to do some very specific modeling. So consider each element of the model in turn. So we have one part of our rod with a temperature T plus dT, say with cross-sectional area A. And there's another portion of the rod, which is in theory attached to it, which has a lower temperature, say temperature T. So it has the same cross-sectional area. Maybe they both have length dx. By the way, the reason we're working with differentials here, T and dt or dt and dx, is because the temperature actually continuously varies through the rod, and so we want to look at an infinitesimally small chunk of the rod, which would have a length of dx and a small temperature change of dt. So let's think about this, try to think about this logically. What do we know? What do we know affects the rate of heat transfer? Just from our intuition. Rate of heat flow. So clearly, or hopefully this is clear, cross-sectional area speeds up heat flow, i.e. more cross-sectional area gives more heat flow. The way to think about this is more pipes for heat to flow through. Another way to think about this in the vibrating molecules picture is you have more contact area between molecules that are vibrating quickly and molecules that are vibrating slowly. So you'll have more energy, or you have more molecules to do the transferring between the two, the hot or the energetic and the not energetic molecules. And so one thing that we can establish from this this intuition that we have is that dq dt, which is the rate of heat flow. By the way, I said we would never do delta T or delta Q. And that's true. We never do delta Q. But we can talk about dq dt. That is the rate at which heat goes from place to place. It should be somehow related to the area, the cross-sectional area. What else? The temperature difference also affects the rate of heat flow. Right? If you have two things that are very close in temperature, the heat won't flow very quickly between them. If you have like an ice cube and a hot iron rod, the heat will flow very quickly. So we get that dq dt. Again, this is the rate of heat flow. Should be somehow related to negative dt. By the way, so dt is if I were to write the absolute value of dt, that is the temperature difference. So why did I stick a negative sign in front? So dq dt tells us the amount of heat leaving the hotter system. So we want to talk about the heat flowing from hot to cold. So if we want to talk about that quantity, we need to talk about how quickly the heat leaves the hotter system. We could have also used plus dt if we were talking about how quickly heat enters the colder system, but we want to talk about the heat flow out from the hotter system because this is our, we have the dt associated with the hotter system here. So the point is that the temperature, the amount of heat leaving the hotter system in a given second, this dq dt, should be proportional to the difference in temperature. And we have a negative sign there just because dt is positive, but we want heat to be leaving the hotter system. So that's just a measured thing that we can do. If we have twice the temperature difference, we would expect twice the rate of heat transfer. Turns out that that's roughly true. Further, a shorter length, if you have heat trying to cross a shorter distance, it should be faster. That should be kind of obvious. It has less distance to cover, so if it moves at a certain rate, then if it has less distance to cover, then it'll cross that distance in faster, i.e. it'll transmit more heat in a given time. This is kind of straightforward. Again, less distance for heat to travel. And so what we can write is we can write dq dt is something like 1 over dx. If dx is small, then the heat transfer rate is large. Now this seems kind of sketchy. We usually don't write dx in a denominator, but I promise this will work out. And then there's also something to be said about different materials conduct heat at a, unfreeze please. Different materials conduct heat at different rates. So we need to account for that somehow. Ceramic, for example, that's not how you spell ceramics. Ceramic insulates from heat better than copper. i.e. ceramic somehow makes heat travel through it more slowly than copper would. So we might write dq dt should be related to K, where the proportionality, it's just a proportionality constant that depends on the material. So basically, K is large for things like copper, K is small for things like ceramic. Higher rate of heat transfer for copper than for ceramic. So we put all these things together. And this K, by the way, accounts for all of the non-proportionality, all of the proportionalities that we were talking about before. So we get dq dt equals negative sign from the dt. It's equal to negative K A dt dx. And voila, we have a differential equation. This T dx, dt dx, this is the temperature gradient. It's basically how quickly, or over how large a distance does, how much does the temperature change if you go over a certain unit distance through an object? This equation, by the way, has a fancy name. It is called the heat equation. And if you take differential equations, which I presume you have to, you're gonna learn to love this thing because it's a very easy differential equation to solve. We're not gonna talk about it. Yeah, so the only difference in relationship here is that you've seen something like dt. Yeah, so how do I want to phrase this? Yeah, this is the heat equation. The ones that you've seen called the heat equation are the same thing, just written in different forms. They are basically the heat equation is a partial differential equation. It relates a single function, say time, or say temperature, to position and time. So you may have seen dt dt equals number times dt dx. And that's the same equation. The reason why, sorry, that's not quite right, but they are the same equation. And you get one by using the, by applying Newton's law of cooling, or yeah, Newton's law of cooling. So basically you'll end up replacing dt dx with something like d squared q dx squared, something like that. And then you'll end up with an equation that looks like dq dt equals number times d squared q dx squared. And that's probably the thing that you've seen. But this is just a different form of the heat equation. Anyway, for our purposes, this equation is overkill. We'll always deal with steady state heat flow, meaning that we have a constant rate of at which energy is flowing, and we will always have the temperature gradient being linear. So if the temperature gradient is linear, that means that dt dx is a constant. And so then we can just say the rate at which the heat is flowing is just equal to a constant. So in particular, when temperature changes linearly from hot to cold, we can instead write so if temperature changes linearly with position, right, then dt dx is a constant. So we can just write dq dt equals minus ka over L delta T. So this L is the distance between hot and cold end. And this is the rate at which heat goes from the hot end to the cold end. And so this is the equation that we're more or less going to be using. Just because it's solving the differential equation that I've given is not straightforward. Well, I mean, it's straightforward, but you guys don't have the tools for it, so we're not going to use that. But it's just for cultural purposes to know what the heat equation looks like. There's another method of of heat transfer, remember we were talking about the three ways of heat transfer. That was conduction. Basically tells us that the rate at which heat transfers is given basically by the difference in temperature between the hot and cold end and the distance that it has to travel. By the way, for those of you who are interested in like custom PCs, that's why your heat sinks have heat pipes. More heat pipes means that you get a larger A here, so you get faster heat travel. And the reason why you want your heat sinks to be close to your CPU is that way then you can minimize L to make the heat transfer even faster. Hence, that's how heat sinks and heat pipes work, or why they're useful. Right, so the second way of heat transfer is called convection. You may have also heard of this. It's used in the culinary industry. You hear things about convection ovens. Convection occurs for both fluids, or it occurs for fluids, rather, like gases. By the way, liquids are also fluids, but it occurs mostly for gases, where, quote unquote, hot particles diffuse into cold particles, or cold regions, and vice versa. So the mathematics for convection, notoriously difficult, like notoriously difficult to handle, so much so that there's a whole study, or there's a whole, any sort of fluid flow is always very difficult to study. There's something called the Navier-Stokes equations, which basically tell you how fluid interacts with itself. And in general, there's a $1 million prize for figuring out whether that equation has unique solutions. It's just very, very hard to study because these systems are very, very chaotic. But we can get an approximate relationship between the rate of heat flow and the temperature difference between a hot and cold thing. This is the rate of heat from the hot to the cold. This is approximately equal to delta T to the 5/4. Note that this is not quite Newton's law of cooling. It's close to it, but it's not quite. So Newton's law of cooling is often a way of saying, okay, well, what is the rate at which the, it says that the heat flow outwards is proportional to the difference in temperature between two things. So Newton's law of cooling is basically this thing. Convection occurs a little bit faster, actually, than Newton's law of cooling. As I'm about to say, in general, convection is faster. And the reason for this should be fairly straightforward. Convection, not convector. The idea here is you have delta T to the 5/4 versus delta T to the 1. 5/4 is obviously greater than 1, so as long as delta T is greater than 1, then you'll have this phenomenon occurring. By the way, a good way to understand, like intuitively grasp why convection is faster, one example of convection would be something like, take a hot cup of water, pour it into a cold bag of water. The hot water is going to cool off very quickly as those hot water molecules diffuse in the cold bag. Whereas if you just put the two bags next to each other, it's going to take significantly more time in order for them to come to the thermal equilibrium. So, I mean, just intuitively, we know that convection, like mixing of fluids, is what convection is occurring faster. And that's why convection ovens, by the way, work so well, because they're basically just ensuring that the surface of whatever substance you're talking about always remains at a certain temperature. And then you have to worry about conduction in the middle. All right, so that takes us through just about to the end of where I wanted to get to. So I will end it there. Does anyone have questions about any of the thermodynamics that we've talked about? We've talked about a lot. We've talked about temperature scales. We've talked about measuring temperature. We've talked about heat capacity. We've talked about latent heat diffusion. We've talked about phase changes. We've talked about heat transfer. We've talked about the heat equation, convection. Any questions? I'm going to end the recording, by the way.